So here we have multiple species example. Multiple species, what do you meaning of multiple? More, like multiple in the sense like 1 2 3 4, like multiples you have. Species in the sense, species are nothing but gaseous, two different gases or multiple gases. When it is getting interacted, what type of chemical reactions are that we are going to calculate here, I mean that reactions, or we can study that. So first I'll make you to understand. So in this workshop, what you're going to analyze? No, you will be analyzing the release of heat and combustion gases from a single car with an engine fire in a well ventilated parking garage. I think some person was asking, sir, I am not able to assign carbon monoxide gas. I think in the first day or second day training he was asking me this. May I know who is this?
I'm Sinan, sir. Mohammed Sinan.
Mohammed, yes. Now you can, today you can see that.
Okay, sir.
Okay.
Okay, sir.
So multiple spaces. In this workshop, you will analyze the release of heat, release of heat and combustion gases from a single car, and with an engine fire in a well ventilated parking garage. The simulation will be run as a steady state analysis. Assume that fire has been reached at a stable, high stage, stable developed stage. Okay. So first I will make you to understand now. So this this is this model which describes. Okay. So this is the model. Now this car was, you can see, there is a car which is a car model which was. This car has parked in the lower ground. Like, when you go for some cinema halls or any kind of restaurant something, you will park your car in the lower ground, right? It is sometimes you will park outside, but sometimes you will park your car in the lower ground. But when you keep on going down, what happens? The humidity will be increased and there will be less air will be present. Okay, humidity will be more and you'll have less air. So what happened? Your car is parked in the lower ground parking garage. You have been parked there, and this car has been reached the heat up to high developed stage. That is, might be, this car has been used for 1 or 2 hours. So when you parked in the underground, some gases were releasing from this car, like heat was releasing. Also in the lower ground you also have some other gases also, nitrogen, oxygen, other gases also. And one more thing, the heat is, along with that, heat is also releasing from this car. Okay. So here we have the symmetric wall, and this is again pressure inlet. From here there is a pressure inlet. This is like one ventilation you have, you can call this as a ventilation. So pressure, air inlet, and jet fans, jet fans and heating, from this heat was releasing from this car. Guys, any doubt?
Sir, from which side air is entering, sir, to inside the room?
Yes, can you see that air outlet, inlet, exhaust you can have, right? So from here the air is entering here. From this
Okay.
ventilation, the air is ventilating. And this car is parked in the lower ground, and in this, from this car, the heat is releasing. Heat will be released, right? After you use, some heat will be generated from this. When you, even the car was, even the engine was not running, definitely the heat will be releasing. So that we know heat and gas releasing from the engine bay, which is of, we will consider that is a mass flow inlet fuel gas. And this is a pressure inlet. So from there is a pressure inlet, and I mean fluid jet inlet, and this is air outlet. Okay, this is our way to your garage, way to your no, the inside portion. And this is the symmetric wall, and rest of the walls are, or rest of the things are walls, all top, bottom, all are wall, all are walls. Okay. So first, so simulation of physical boundary conditions, mixture of what sort of mixture was happening in the, in the boundary, I mean here in the parking garage, which is mixture of nitrogen, oxygen, carbon dioxide, and also a form of H2O. And 6 meter per second, this is exhaust. From here there is exhaust now. The way air is getting exhausted, which 6 meter per second it is getting exhaust. And 80 Newton per meter cube movement of source from here, from the source jet in, no, from this area which is having jet in, no, from that is 80 Newton per meter cube from the jet ins. and kg per second of fuel gases, that is H2 and C2O, at a temperature of 1200 Kelvin. Okay, that is of 1200 Kelvin we have. From where? From this area. 1200, one is CO2, and what do you have? CO2 and as well as water vapor, water CH2 and CO2, which is a temperature of 1200 Kelvin, that no, from the car, which has been releasing from that car. Okay, and we are solving this problem as K epsilon turbulence model, and also we are using a type of radiation model using the method called WSGGM method for absorption of coefficient. Absorption coefficient we are going to calculate. The inlet temperature is at 300 Kelvin. So using taking all these parameters as an input, we are going to solve the problem. So even this is also will take at least 40 to 30 minutes. Okay, so I'll go with here fluid flow fluent. Okay, so you can mention this as a multiple species. Multiple species I'm going to use. I'm going to use it this. You can try to open that file. Because sometimes the file will not get open in your newer versions. So even I will share you this, the total, what you say, results file I will share you. You can try while you're teaching to the students, you can also discuss with this. Okay, so I'll take it here, the mesh file, right click. If it is open, it's fine. Otherwise, you let me know so that I'll share you the results files also. You can take this, the garage part, garage, you can take it and go to the setup. So just try to go with the double precision. I'm going to with this. Okay, so that's the model we have. So first I'll make you to understand which was designed accordingly. So go to the display, you can undo all these things. I'm going to undo all this. So first I'll make you to understand inlet exhaust. So this is the exhaust portion. I think it will be like this. Okay, and mass flow of this, this is a car from this, and pressure inlet, this we can take. This is one pressure inlet we have, and symmetry, this is the symmetry wall, you can take it here, and this is the wall pressure. This all are walls. Okay, this is the first one is inlet exhaust and wall car. So this all are wall cars which has been defined, and this is like mass flow inlet of gas. Okay, wall ceiling, the top one. Okay, wall floor, so bottom is your wall floor. Okay, the bottom is a wall floor, and the wall jet. So this is like from here the air will be entering, you can see. I'll show you this so that you will able to understand. You can zoom out. Okay, this way you have it. Okay, this way you have, and wall jet housing, this is like the outside portion. So from here there is inlet, you can consider this is right, this way you have. So I hope you all understood this, what are the names it has been given. Okay, and next case is, so I am going to use just go with I'm not going to use scale, which is already in terms of in meters. Just go with check the quality, and you can go with the report quality. So everything is fine. Now it is pressure based, okay, absolute, and I'm going to act gravity. Now you have to tell me along which direction I have to apply the gravity. Either I have to apply in the x direction, y direction, or z direction. In which way I have to apply the gravity according to my object?
Minus Z, sir.
Yes, z direction. So z direction, I'm going to define the gravity. Okay, so this way I'm going to apply, which is of minus 9.81. I'm going to apply the gravity, right? So once we have defined this, then what could be the next step? So here you can go with the models. So in that you can go with your model of viscous k epsilon. So in that you can go with here k omega, which around the wall treatment I'm going to use it here, right? And it is a multi-phase, so go with multi-phases. So here we have the mixture, no? You can go with the mixture. So how many mixtures we have? One is nitrogen, oxygen. So how many mixtures you have there? One is nitrogen, oxygen, carbon dioxide. 1, 2, 3, 4. 4 mixtures you have. Okay. So we can have, first what I do is, instead of this multiple phases, then I'll go with here a radiation DO method. I'm going to use it. Ordinate method I'm going to use it. I'm going to define it. So when you activate radiation, automatically this energy will be going to be activated. Okay. So now see, energy previously energy was in off condition. You see here. So when you activate this radiation model, automatically is going to be activated. Discrete ordinate method I'm going to use it. So energy iteration per radiation is how many iterations? 1 iteration I'm going, not 10, which should be less. I'm going to use it. Right now available metal properties or methods has been changed. Please confirm the property before. Okay, fine. You see, automatically the energy is also got activated. You can observe that. Okay, so this you can have. Now go for the species. This is multiple phase. I'll go with the species model. You can go with the species. Here you can go with the species transport. In that you can go with your mixture template. What sort of, no? See now sir, you will get a doubt, sir. Like I want to take a fuel tank. In the fuel tank definitely there will be fuel and air. No, you have to put the mixture template. Mostly, I want to solve both, gas or air. You can take fuel, oil, air. So ethane or air, diesel, air, you can take it here. You can solve one diesel tank. You can solve the analysis also. Diesel, air, inlet mixture, benzene here. There are different mixtures. Okay. But what happened for our bikes? What sort of petrol and air would be there, right? You can take a petrol. Okay, both from here you can take it here. Different. It will be have different templates. No, sir, I want to edit this mixture template. Then you can go with here. You can edit here. What sort of mixture template you want to add? You can edit that, right? So default you will have some templates. From here you can take it here. All right, methane alcohol here, methane air, kerosene air, no, gas oil air, fuel air. Okay, you can have here. So diesel air, you have different cases. Carbon monoxide here. I'll go for mixture templates. View. I'm going to use it here. So try to give, apply, and try to give. Okay, I'm going to use it here. So now go for the materials. So in that materials, already mixture was added, right? So mixture was added here. So click on this materials. So mixture which is having nitrogen, oxygen and water. So one more thing is missing. Which one is that? Carbon dioxide, which is missing now. Go for mixtures, create or edit. So here you can put it to fluids. You can put it to fluids. So in that Fluent database, from there you can copy this. Okay, carbon dioxide you can copy. Carbon monoxide was there. Carbon dioxide will be there. Okay, you can put it here. Mixer template, create or edit. So change type to fluids. No. First you can. I'll add it Fluent database. Change type to fluids. Fluent database. So carbon monoxide. Carbon monoxide was there. CO2 carbon dioxide is different. Carbon monoxide is different. So first I'll copy
Sir,
it.
can we change? Hello.
Yes, yes. Yes, yes, you
Sir,
can change it now. Sorry, you
in
can put it
material
your
type.
fluids. Here you can change it. I forgot that. Might be here you can have. You can go with here. C. I hope it will be there. Carbon dioxide. You can see carbon dioxide. You can try to copy this. Okay. So you can see both. Try to close it, and you can close it. Here it has been added in the fluids. It has been added, but it should be added here. Right click here. You can delete it. The mixtures. Create or edit. Again it is adding in the fluids. Not a problem, we'll copy it now. We'll copy it. Just try to close it. Okay, so first you change the properties of this. So here once we do know, click on this mixture template, then we can give the names thermal conductivity and all. So how much we have? Yes, thermal conductivity is 0.054. I'm going to use it here. Fluent database. Once we copy this, then what you can do is once you copy this carbon dioxide, no, again go for here, copy these conditions. How we can copy it? So go for mixture templates, no, create edit. So you have already you have no species mixture species where no go for edit here. See what was there previously? It was having nitrogen, oxygen, water. So nitrogen, oxygen, water you have no water or so carbon dioxide. Just go with add it here. So it will be added here, right? So it is going to be added. You can see carbon dioxide will be added there. And this way you can change it here. Now again the properties of the mixture template I want to change it. So mixture template, create or edit. So in that thermal conductivity I'm going to change it here. Thermal conductivity here I'm going to use it. Instead of constant I'll go with here mass weightage mixing law. I'm going to use it. And viscosity I'm going to change it this also mass mixing law. I'm going to use it here. And using here it was mentioned what method we have to solve using WSSGGA method, radiation DO radiation model with WSGG for absorption coefficient. So I'm going to use it. So in WSSGG method you can go domain based. Once you're done, try to close it here. So this bin we have been changed here. Now already the default was aluminum was there, but what these walls are made up of concrete, right? I mean it has been created with respect to concrete. It is not made up of aluminum. These walls are. So I have to create one more concrete material. So go with solid. I mean this you can know aluminum created it. So you rename this. Okay, so you rename this as concrete. I'll tell you, sir, why you are editing this aluminum. I'll tell you. I'm not editing this aluminum. I'm just concrete. Okay, let's change this property to concrete. You can give it here. Uh, Concrete. I'm going to use it here. Okay, just rename it. But I'm going to give properties now. What are the properties of this concrete? I'm going to use it because the property which is not mentioned in the PPT. Please note down this density which is of 2400. And specific heat I'm going to use it 1000, and thermal conductivity of this is 2.1. and once we're done change, if I give change or create, so if you give yes, what happened? Aluminum is going to be changes. If I give yes, aluminum is going to be changed. I'll go for no. So what happened? Both will be there. Concrete will be there, aluminum will be there. Okay, so this way you have to do the changes. Yes, sir. Once we define this, then I'm going to give the boundary conditions or cell zone conditions. So in that you have fluid jet in. So edit. So which parameter you are assigning, sir? I am going to assign this parameter of this 60 Newton per meter in the source jet. This I am going to assign it. So fluid jet in. Go for edit. So you can go with here source term. You can activate this. So here you can activate this. In that y movement which is having 80, just activate this. So put it to constant. I'm going to give it this minus 80 Newton per meter cube. I'm going to use it this. Okay, this I've been given it. I hope you understood what I'm giving here. Now go to the boundary conditions. So in the boundary conditions, so inlet exhaust, how much it was, which is having 6 meter per second is the exhaust. So that I'm going to give it here. Inlet exhaust, edit it. So in that you can go with here magnitude with normal to boundary, which is having minus 6 meter per second, which is having exhaust. And because I doesn't know intensity viscous flow, I know, but intensity I don't like, I doesn't know. I'll go with intensity viscous ratio, which is intensity 5%. Viscous ratio is also, I'll go with 5 ratio. I'm going to use it this. Just go with OK. Now the next case is you can go with here pressure inlet. Pressure inlet is from, this is your pressure inlet. So go with pressure inlet, edit it. So in that already we gave it, right? Inlet exhaust we gave it. Okay, this is a pressure inlet. You can go with here, edit it. So this is also, I'll go with here pressure, which is, I'll go with intensity viscous ratio 5, and this is also 5. I'm going to use it here. And the temperature, which is already mentioned, that is 295 293.15 Kelvin. I'm going to use it there. Okay, so this inputs I have given here. Now next case is pressure inlet. We have the species pressure inlet. Radiation. So black body radiation, no. So this is 293.15. Indian MCT. I'm going to give this one. So next is at the inlet region itself. Again we have different cases. One is air and species. You can go with that. So which is having I'm going to give this oxygen as 0.3. So both should be equals to 1, that is 100%. 0.23 and other one will be 0.71. It will be 0.71. It will be there. So when you add this 0.73 plus 0.63, if you add, it should be equals to 1 should be there. Nitrogen and oxygen should be equals to 1. That is like we have mass fraction, right? Mole fraction, mass fraction. While we are studying in our chemistry, we have this mole fraction, mass fraction should be equals to 1. So that we have been defining here. Okay. So once we have given this, then you can go with your mass flow. Mass flow, from where you are getting this mass flow? From the car. So go with edit. So then from the car, then I will go with absolute. Mass flow is of 0.1. I'm going to use it 0.1, and that is of direction normal to boundary. I'm going to use it. In intensity and viscosity, that is of 5, and this is also I'm going to use 5%. And species, and yeah, so nitrogen and oxygen we have. So I'm going to define it. Now specify the mole fractions. I'm going to give it here. Okay. So first I'll define the thermal, which is having 1200 degrees. That's what, right? 1200 kelvins. Okay. H2. So here we can go with a thermal. So instead of oxygen, I'll go with nitrogen because we already defined there, right? So this I'm going to use it. How much it was? H2 was 0.65. Okay. So CO2, which is of 0.3, I'm not going to use it. Nitrogen will define 0.35 over there. So when you add this 0.35, 0.65, this it should be equals to 1. That's what I gave it here. So that is the mole fraction equation. So what is the next step? Already we have given temperature and all. So go with walls, no? To the walls. Walls are made up of concrete, right? So movement, thermal, you can put it to concrete. I'll put it to concrete. Temperature, you can put it concrete. So which is having 0. MCD is, it is not a black body, which should be less than 1%. Wall thickness, we can give it here 0.3. I'm going to use it. And heat generation over there, conduction, we can give it here and try to give OK. So not a problem. So here we can give it here, edit it, yes, 0.3. temperature we have given concrete as a material, try to give OK. So now whatever the walls we have, no, whatever the names are the walls, excluding this car, wall ceiling, wall floor, wall jet, all are made up of concrete. No, I'll go for walls, copy. So from the wall to which cases you want to copy? I want to copy to wall 2, wall ceiling is the top one and wall floor is the bottom one. Okay, try to copy this. Whatever the inputs you give to the wall have been copied to the rest of the walls, right? So then go with operating conditions. In that, yeah, specify the operating density also. I'm going to use it. Okay, so try to give this inputs. Yeah, the pressure is of 1 bar. Again, you can save it, save the project. Even this is also will take at least, we can go with here Fluent, multiple spaces you can take. I'm going to save it as okay. So once we are given the operating conditions, then I'll go over here solution methods. I'll go with here pressure is body force, simple. I'm going to use it here, body force, the average. We can go movement, which is having first order, because we doesn't require that. We'll go first order. Turbulent kinetic energy, because we doesn't require movement and all this stuff. First order, let it be this. And rest of the things, energy should be in second order. Yes, nitrogen second order, oxygen second order. I'm going to use it. And go to the solution controls, and pressure is of 0.3, density, body force, this I have given here. So once we define, then you can go with your solution monitors. Sir, what do you mean these solution monitors? So you can go with here, I can go with here edit. What sort of solution monitors? Because we doesn't require velocity and all this stuff, right? You can put it to none also, because we can reduce the time cycle. Okay, now I'll go for here create. So in the create, no, even plot it. What you want to see the results? I want to see the mass flow rate. You can go with here mass flow rate. Flow rate you can give. So mass flow rate. So at which region you want to see mass flow rate? No, you can put it here mass flow rate. So at which region you want to see? I want to see the mass flow rate at velocity jet in. Over here this jet in, I want to see the mass flow rate. So even you want to write it, then I want to give OK, this area. Then sir, I want to see the heat also. I want to see the heat things also. So go with again create one more thing, plot it. What heat flux I want to see? What is mean by heat flux? The amount of heat transfer per unit cross section area. Heat flux I'm going to use it. Okay, so you can change it here, heat report type into here you can put it here, wall fluxes. In that you can go with your total heat flux. You can have total surface heat flux or radiation heat flux. What input parameter you want to see? Total surface heat flux we can take it. Total you can at which region, sir? At which region you want to see? For example, I'll go with wall floor. Wall floor I want to see that. Even you want to write it that, you can just write it. So both the things I want to calculate. Okay, so go with initializations, standard initializations. So from where you want to compute? So you can take it here. You can see it, no? So gauge which is having turbulent dissipation rate, we can have turbulent, this is not that much required. I'll go for changing this value 0.01. Turbulent dissipation rate also 0.01, which is we doesn't require all this. Okay, and yeah, let it be this. Initial values is 0. So once we given this, okay, so H2O is 0, you can have, and O2 is, we have given already, we mentioned, but here it's showing 0.23, and yes, the temperature is 300. So once we given, try to initialize this, try to initialize it. Yes, we've been initialized. Now I want to calculate the results. Okay, you can go for run the calculations. This time I'll go with some 500 iterations. 500 iterations, try to calculate it. It will take a lot of time, not a problem, because I can reduce it, because the solution will not get converged, but in this 1500 iteration we can see the temperature.
So it will take almost 1 hour, sir, to solve.
1 hour, because I am not giving that much iterations. If you want to get solution, get iteration, at least you should go with more than 2000, 3000 iterations.
Okay.
We'll see it, not a problem. If it is get iterated within less time, also fine. It will take a lot of time.
I solved, sir, like 3 days back. It took almost 1 hour or something.
This was your second training or what?
Second trainings.
So from where did you go trained?
CAD only.
From where?
CAD center, sir. CAD
Okay,
center.
CAD center. I hope Milton was gave you the training or what?
Ah, yes, sir.
Okay. So all your doubts was cleared, or you have any pending again?
This problem, it was showing some error, like it was not proper answer what I got.
Sometimes what happen? No, solution get diverged or something. It will shows energy will get divergent. Solution with convergence get divergent. It shows us. You can see it. Even I have results files also. We can take it that, or we can go with this also. Anyway, it's fine. We'll see it. See, still it was in the iteration 3 only. We gave 500. So you assume how much time it will take. So meanwhile what I do is I'll take the results. Okay, so let it get solved. So you can take the you can take one more fluid flow fluent. Okay, so I'll import the results. No? You can try to import case, browse it, which is already I have solved this problem. Okay, I have that results. I'm going to take it that. Or what we can do is, instead of this, I import the case file. We can take, here you can see that case file you have. We can take this. But what about the results? Okay, so let it be, because I want to see the results up to here itself. You can go with this. I'll stop it here up to the iterations of 7. I'll just stop it here. Just go with here, cancel, because already some results will be saved up to iteration 7. The results will be saved. I want to see the results up to there. Okay, so you save it, this file, you can save it, save the project up to 7th iteration. You want to see that, because better to go with up to 500 iterations, but it will consume lot of time, but I'm not going with that. You can go with this, even we can see the results. Interrupted the client. You can see .dat file, you can see here, right? Writing the zip. Okay, so what you can do is, I'm going to take fluid flow fluent. So in that you can take the setup, right click here, import, browse. So where you've been saved in the fluent, right? Here. So here we've been saved, I hope. So here you can take this. Even you have results files also. Solutions, import the final data. You can put it to all files. Okay. I think the dat file was not saved, I hope. So go with here, we can see it. Go with fluent, we'll see it, is that files has been saved or not. We'll cross check it that. Yes, this is a case file, but results file, not .dat file was not saved. Because we stop exactly in the middle now. Not a problem. We'll go with this, because all inputs will be there, because we saved it, right? Whatever inputs was there, it will be saved. Up to at least we'll go with the iterations of 10. Well, then we'll do it. See, whatever inputs you gave it, as it is, it was there. So initialize, standard initialization. 0.01, and this is turbulent display, this is also 0.01. So using these inputs, again I'm trying to install it. Okay, make sure that you should have the results file, otherwise you cannot see the results. Okay, just run the calculations. At least I'll go with some 25 iterations. I think one more thing we missed is monitors. We have done 8 flux and things we have missed. Let it be solved. I will see it, no, the results files has been saving or not. You can cross check it, no. I will go with here. When it is not saving, later we can save it, no. See, the results has to save .dazz. You can save it. I'll go for 10 iterations. You can see that. Okay, I'll stop it here, guys. You please observe it. Just stop it. Up to 10 I went. Okay, you can go with up to 200 300 because it will take almost 1 hour to consume. Okay, so let it get okay, just go with here, file, save the project. You see it is saving this file we required, .datz file we required. Okay, dot, last time what I did it, I just made cancel, that's the reason it has been not saved. See, .daz dot file, results file, these are the results files. Right, so it has been saved. I hope, let it be saved in. We'll see it one more time. The Fluent, you can go with this symphonic model. This we can have. Now you see this are all results, all it has been saved, this all, no. Now see dot dat file dot I think this is symphonic, sorry. We can have heat multiple spaces. You see, now DAT file. This is your output file, .dat. Please respond anyone. Have you observing this? Sahil,
Yeah.
Kishore?
Yes, sir.
Yeah. Yes,
Yes.
sir.
So previously only we have case file. Now we have seen dot file also. Now you see what is the memory of that, which is we have results on that. So try to close it. Now even sir, can I with respect to 10 iterations, can I see the results? Yes, why not? We can see the results also. Reports, what you want to see. Then you can go with fluxes setup. I want to see what you want to see. I want to see the mass flow rate of what. For example, I'm selecting all of them. You can just compute it. So which is approximately 0.00. Okay, you can see what would be the radiation, total heat transfer rate or radiation rate, how much we have. Just try to compute it. So approximately, which is very high, you see 1549 we get. Okay, so we can have. Now I'll be closing this. Okay, you can close it. Now sir, how do I check the results? Because it is saved over here, no? So what I do is, again you take a Fluent window, because we have results, no? Now we doesn't know. Go for setup, right click here. Now go for import case file, browse it. So that's the case file. Okay, so I'm going to take it. Which file we have, either we have opened in the proper order or not. Import, browse it. So multiple species, right? I'm taking this. Okay, so just you can take it. So again in solution, click it here, right click, import the final data, browse it. Here you can go with this species. In that you can take it dot, you can see dot dat file, results file, you can take it that, right? Both will be green tick mark. Now sir, how do I check the results, sir? Because if I open this again, it will open the Fluent. Then you can go with here results, click it on this results, try to browse this result and put it in the results. Okay, you can try to put it in the results. Now you can open in the CFD post process, you can see that. Okay, so this way we have. Now we will see the different cases now. So there are different walls. I'll put it all these walls as one surface. So how do we create? Location, you can have location, surface group you can make, surface group, walls you can change, walls try to create. So which all walls you want to make as one group? So you can go for here, you can go for locations, all domains. So which all groups you want to make it? So in that, wall is one, this, and wall car is this. Just use control, wall car, wall ceiling, wall floor, you can use it, wall jet housing, you can take it. This all you can put it as one group. Okay, wall car, wall ceiling, wall floor, wall jet, 1 3 1 2 3 4. Okay, one is wall, the next one is wall car, wall ceiling, we have wall floor, wall jet housing, and wall jet. This is also, all this I'll put it into one group. Okay, just try to apply it. Sir, why you made all this one group? Because see, if I made one group in the single shot, you can have all in one group. Okay, so that's the reason I made one group. Now sir, I want to check the temperature, sir. Then how do I check? So go with here in the walls itself, click it on this walls. So go for here, color. So constant or variable, what variable? You can put it to temperature variable, temperature. So minimum it was showing, no? So once you try to apply this. Okay, temperature global, you can have, try to apply this. You want to see the temperature, you can see the mostly over here. Here we have 1200. Oh yeah. So what you do is this default, you can go with here, edit it, legend the thing, you can have appearance, put it to scientific, fixed you can put it, or 4 digits you can put it, try to apply. So approximately we have 1200, no, 12.03.40 you have, so that region maximum over there. Okay, so this way you have. And then you can create one more surface. Sir, my intention is, no sir, you show me all these walls, but I want to see exactly over this region. See, exactly I want to see over this region, guys, this area. I want to see at that region. So I want to have look. So how do we create? Just you create one surface over there. Okay, location. You can go with ISO surface. What surface name? You can give any name for to this. So for example, I am giving this as with respect to over here XZ plane. You can create with respect to XZ plane. I am going to create over this region. I am creating it, right? So you have created. Sir, wait, what region, sir? Because the whole length we doesn't know, right? How can I create? So you can give. I'll mention this. The total distance is 18 meters. Now I'll put it to 9 exactly in the center. Okay, along with respect to what? Along with respect to y direction. You can have y direction because along y direction, right? This is x and this is z. Along y direction, I want to create. So I'll go to create that. So color variable, I'll go with this. Variable, what you want to see? The variable, I'll go with the temperature. Okay, variable of temperature, I want to see that. Okay, so once we define this, try to show faces also, color show faces, let it be. So try to apply this over that region. Now you can undo this walls, only that area. You see how much temperature we have there. Okay, this area. I hope you can understand how it was happening. Okay, now this time I want to see the gaseous. Sir, you have given nitrogen oxide, that gases I want to see, sir. Sir, how do I check it? So this walls itself, we can go with this. So you can undo this XY plane and go for walls, and I want to see that walls, or you want to create a new one. Okay, let it be this, let it be this. So you create a new one. So what you want to create? ISO surface, location ISO surface, which we know ISO surface. So this time I'll go with here gas. I'll go with this. Okay, so you can create a name there. So what sort of thing now? Geometry, color, you can go with your variable. So you can go with your color constant was there, let it be constant color. So render style, lightings and all stuff you have, view you can give it here. Yeah, let it be this geometry. So variable, you can go with your CO2 or what sort of gas you want to take it. For example, I take it CO2 because CO2 I want to see CO2 mass fraction, how it was. Still it is getting loaded, but here it is not showing. So instead of CO2, I want to see, because you see there is a color which was getting from here. Can you see some ash color, guys, from here? I hope you can have observed. So sir, can I change the color, sir?
Yes,
You can change the color. Now you can put it some other color which look apply it. I can just put it here the color. You can see, you can have a idea of that how it was. No, from here. Now sir, I want to see for other gases also, sir. Sir, how do I check it? Here you can put it to geometry. Instead of CO2, I'll go with nitrogen or something. Nitrogen mass fraction. How it was. See, this is about nitrogen. Nitrogen cases. And what about oxygen? You can go with oxygen mass fraction. Over here we have from there, right? Like this you can go with here. Now sir, I want to accept this, sir, can I go with any sort of streamlines? Yes, you can go with your 3D streamlines. You can go with here streamlines. This is like particles or 3D streamlines. You can go with this. So any name you can apply this, like I'll give it here streamlines, let it be streamlines. Okay, I'm going to use it this. So you can handle this gases streamlines. So starting from where? No, I'll start from inlet. From this is our inlet, right? So starting from inlet, which is our inlet. Inlet exhaust we have, yes, this region. And samples of how many we can go? Equal sample. For example, I'll go with 100 samples. Let me check. And means what velocity? Yes, let it be velocity. We can have. Okay, so direction I can go with backward direction. We can have cross periodic, let it be this. Color, what sort of color you want to see? Color, let it be variable. I'll go with here, let it be temperature. We have, you can have look. So you want to give any range, you can give the user specified, you can give the range. Like I want to see for 300 approximately to 400 Kelvin, between this I want to see that. Okay, so color is under define, you can put it the color, so you can change it, try to apply it. You can see the streamlines, how it is passing. So these are the streamlines. Okay, so how it has been changing. Sir, can I see like any kind of gas kind of color, kind of gas, how it will be there? You can undo the streamlines. You can go with your volume, volume rendering. You can go with your volume rendering. Okay, so you can have gas volume. You can take gas volume. You can take the gas volume. So in that, what sort of all domains? So here I'll go with here, instead of I'll go with here nitrogen. I'll take it here. Nitrogen, I'm going to use nitrogen mass fraction. So resolution is 20 fine, and the transparency, okay, let it be this. Let me just try to plot it. You can see some kind of color, you can see there. Okay, still it's getting loaded. You see guys, a small color, can you see that? Have you observed? I'll increase this transparency.
Yeah, sir.
This area, you observe it guys, from this area. You are watching, right? This area, a kind of blue color which was hiding, no color.
Yes, sir.
So this way you have. No, sir. Can I go with other color like O to mass fraction? You can see there. This is the values are important. You can go now. O2 is everywhere here. And other thing, no night mass fractions, or we have pressure kind of thing. You can have look. I hope pressure will not be there. I hope. Let me roll. Even pressure is also have gas volume pressure we have. Okay, this way you can check it. Okay, any doubts, any queries you want to ask, please ask me so that I'll explain you. Okay, so will you try this?
Yes, sir.
Yes, sir.
Okay, I'll stop it here. Please practice it. Then you can ask me the doubts. So tomorrow it could be the doubt clarification session. Till now we was done with our training part.